Welcome students for the chemistry lecture B.Sc. Part 2. Up till now we have seen the electrolytic conductivity chapter, and in this lecture again we are going to see the Kohlrausch law and its application. Here in this chapter you have studied what is the electrochemistry, and electrochemistry, it begins with the study of conductance, and it is mainly related with the transformation of chemical energy into electrical energy and electrical energy into chemical energy. And conductance, it is the capacity of any conductor for the passage of electricity. You have studied this. Then you have studied types of conductors. There are two types of conductors, metallic and electrolytic. And while the passage of electricity takes place in metallic conductor, there will not take place any change in the material of the conductor, and electricity flows with the help of free electrons. And in case of electrolytic conductors, electricity flows through the migration of ions. These are the two types of electrodes. And conductance, it mainly depends on temperature and the number of ions present in the solutions. Again, we have seen the different examples of the metallic conductor, as all the metals, they are good conductors of electricity, and electrolytic conductors are the fused salts, strong acids, strong bases, and their aqueous solutions. Then in this chapter we have studied what is the resistance, what is the conductance, what is the specific resistance, then what is the equivalent conductance, molar conductance, then variation of the conductance with concentration or with dilution. And dilution, it is nothing but decrease in concentration, and how the conductance varies with the dilution we have studied in the last lecture. And our today's point, it is the Kohlrausch law and its applications. Kohlrausch, he is a scientist. He studied the conductivities of large number of strong electrolytes, and he found an interesting relationship in between the conductivities, and he formulated his law as a Kohlrausch law. The statement of the Kohlrausch law is, when the dissociation is complete, each ion makes a definite contribution towards equivalent conductance of the electrolyte, irrespective of the nature of the ion which it is associated, and the value of equivalent conductance at infinite dilution of any electrolyte is the sum of contribution of its constituent ions. Here I would like to give you some examples that have studied the Kohlrausch in his experiments. Kohlrausch found, when he used electrolyte as a KBr, then the lambda infinity value of KBr is 0.15192. I will repeat once again. When electrolyte KBr is used and Kohlrausch measured its equivalent conductance, then he observed the value lambda 0 equal to 0.01592. And in case of KCl electrolyte, the lambda 0 value, it is 0.014986. And here anions are different, but cations are same, and the difference in lambda 0 value, it is equal to 0.00206. Then in the next time he used a NaBr electrolyte and NaCl electrolyte, and the conductivities he found as 0.012851 for NaBr, and NaCl lambda 0, it is equal to 0.01265, and he observed the same difference in between these two, that is 0.00206. His third electrolyte pair is LiBr lithium bromide and lithium chloride, and their lambda 0 values are 0.011709 and 0.011503. Again he observed the difference, and that difference it is equal to 0.00206. And in these three pairs, the nature of the electrolyte is cation same and anion difference. And again he tried for the anions same and cations different, and he used the same electrolytes as KCl, NaCl, KBr, NaBr, then KNO3 and NaNO3. He measured the lambda 0 values and he found the same difference, and that difference is 0.02341. The pair nature, it is the anion same and cation difference, and these observations lead to the Kohlrausch to make his law, as each ion it contributes independently for the electrolytic conductivity. Either that conductivity is a molar or equivalent conductivity, and this is the explanation of Kohlrausch law. Once again, I will I will told you the statement of the Kohlrausch law. At infinite dilution, when dissociation is complete, each ion makes a definite contribution towards equivalent conductance of the electrolyte, irrespective of the nature of the ion with which it is associated, and the value of equivalent conductance at infinite dilution of any electrolyte is the sum of contribution of its constituent ions. Then, and he formulated his law in 1874, and this is the law of independent migration of the ions. Mathematically, the Kohlrausch law, it is given as given by this equation: lambda 0, that means equivalent conductance of any electrolyte at infinite dilution, it is equal to lambda 0 plus lambda 0 minus, where lambda 0, it is the equivalent conductance at infinite dilution, and lambda 0 plus, it is the ionic conductivity of cation at infinite dilution, and lambda 0 minus, it is the ionic conductivity of anion at infinite dilution. This is the mathematical expression of Kohlrausch law. Then, according to Kohlrausch law, a limiting equivalent conductance values of acetic acid, sodium acetate, HCl and NaCl can be written as follows. I repeat once again, according to Kohlrausch law, the limiting or infinite values of equivalent conductance for acetic acid, sodium acetate, hydrochloric acid and NaCl can be written as follows. Here the lambda 0 of acetic acid, it is equal to lambda 0 of acetate ion. That means CH3COO minus ion plus lambda 0 H plus. Then lambda 0 of CH3COO-Na, it is equal to CH3COO minus ion plus lambda 0 of Na plus ion. Then lambda 0 of HCl, it is written as lambda 0 H plus lambda 0 Cl minus, and lambda 0 NaCl, it is equal to lambda 0 Na plus lambda 0 Cl minus. And the Kohlrausch law, it is used to determine the equivalent conductance of weak acids. Suppose, for example, we have to determine the lambda 0 of CH3COOH, that means acetic acid. Then what we have to do is, for determining the lambda 0 of acetic acid, we have to sum up the lambda 0 of sodium acetate and HCl, and from this sum we have to subtract lambda 0 of NaCl, and by cancelling the common ions we can have at the last in lambda 0 of NaCl, it is equal to lambda 0 Na plus lambda 0 Cl minus. And this is the most important application of Kohlrausch in the determination of equivalent conductance at infinite dilution of weak electrolytes. We have seen this application in the last video also. Then another application of the Kohlrausch law, here calculation of degree of dissociation and calculation of dissociation constant for weak electrolytes, and the next application, calculation of solubility of sparingly soluble salts. Let us see how the degree of dissociation it is calculated. You know, alpha, it is the degree of dissociation, and one here alpha, it is the degree of dissociation, and according to Arrhenius theory of electrolytic dissociation, the increase in molar conductivity with dilution is entirely due to increase in the dissociation of electrolyte. The molar conductivity at infinite dilution being maximum because the dissociation is almost complete. Thus, if the molar conductivity or equivalent conductivity of solution at any concentration C and the molar conductivity at infinite dilution, that is zero concentration, we will have the degree of dissociation, it is the ratio of the number of dissociated ions, that means lambda 0 at any certain dilution divided by number of total ions present at the infinite dilution, and this ratio gives us the degree of dissociation. In short, we can find the degree of dissociation by using the formula alpha, it is equal to lambda phi divided by lambda infinity, where lambda phi, it is the equivalent conductance at certain phi dilution, and the lambda infinity, it is the equivalent conductance at infinite dilution. This relationship is found to hold good only for weak electrolytes. The value for the weak electrolyte can be calculated using the Kohlrausch law, as already we have discussed in the first application. Then in the determination of calculation of dissociation constant, here in case of weak electrolytes, knowing the degree of dissociation, the dissociation constant K of weak electrolyte at a concentration C of the solution can be calculated by using the formula here Kc, that means dissociation constant for C concentration, it is equal to C concentration into alpha square, where alpha it is the degree of dissociation divided by 1 minus alpha, and this is the very simple formula in the determination of dissociation constant. Here Kc or Ka or Kb. Ka for dissociation constant of acids and Kb for dissociation constant of bases. By using this formula, C into alpha square divided by 1 minus alpha, where alpha it is the degree of dissociation and C it is the concentration. We can find the dissociation constant. Then the next application of Kohlrausch law, it is in the calculation of solubility of sparingly soluble salts. And you know that the salts which have negligible solubility in the water, they are called as sparingly soluble salts. For example, silver chloride, barium sulfate, lead sulfate, etc. These salts are sparingly soluble salts and they dissolve to a very small extent in the water, and these salts we call as a sparingly soluble salts. And with the application of Kohlrausch law, we can determine the solubility of the sparingly soluble salts, and it is again very simple method. Here these salts they dissolve very little in a water and their solutions are considered as infinitely diluted. Further, as their solutions are saturated, their concentration is equal to their solubility. In case of only sparingly soluble salts, their solutions are saturated and their concentration is equal to their solubility. Thus, by determining the specific conductivity kappa and the molar conductivity of such a solution, we have lambda 0 m, that is the molar conductance at infinite dilution, it is equal to kappa into 1000 divided by molarity, and molarity it is nothing but number of moles of the solute present in a 1000 ml, and therefore we can write here specific conductance into 1000 divided by solubility, because we have considered the concentration of sparingly soluble salt, it is equal to the solubility. Therefore, here concentration, molarity, we have substituted by solubility. Therefore, by using this equation, we can find the solubility, it is equal to specific conductance into 1000 divided by lambda 0 m, where lambda 0 m it is the molar conductance at infinite dilution. Similarly, we can find the equivalent conductance at infinite dilution by putting lambda 0 here. Simply lambda 0 m stands for molar conductance. Then Again, I will explain you the how Kohlrausch law is used for the determination of molar conductance of weak electrolyte at infinite dilution. You know, weak electrolyte are not completely ionized at any dilution. Therefore, their equivalent or molar conductance cannot be determined experimentally. So, their molar or equivalent conductance at infinite dilution can be calculated by using Kohlrausch law. Here, the molar conductivity of Kohlrausch law can be calculated by using Kohlrausch law, and already we have seen that the lambda 0 of CH3COOH, it is equal to lambda 0 of acetate ion plus lambda 0 of H plus ion. Let it is our equation number 1. The above equation can be obtained by knowing the molar conductivity at infinite dilution for strong electrolyte like sodium acetate also. Here again we can write here lambda 0 of CH3CONA, it is equal to lambda 0 of acetate ion plus lambda 0 of Na plus ion. Let it is our equation number 2, and lambda 0 of HCl, it is equal to lambda 0 H plus lambda 0 of Cl minus. That it is our equation number 3, and adding equation number 2 and 3 and subtracting equation number 4. Here we have added equation number 2 and 3 and subtracted equation number 4. We get here lambda 0 CH3COO plus lambda 0 H plus, and this is the equation of lambda 0 of acetic acid. That means by knowing the equivalent conductances of strong electrolytes, adding some electrolytes and subtracting some particular electrolytes, we can find the lambda 0 of any weak electrolyte, and by using this method we can find the either molar conductivity or equivalent conductivity at infinite dilution of weak acids. Then the next application here in the determination of ionic product of the water. Kohlrausch law, it is used in the determination of ionic product of water. You know, water, it has formula H2O, and it ionizes into H plus plus OH minus, and in case of pure water the concentration of H plus ion, it is equal to concentration of OH minus ion, and the ionic product of water is represented by symbol Kw, and it is given by Kw, it is equal to concentration of H plus ion into concentration of OH minus ion. Here we have used square brackets for the concentration, and here we have written C stands for concentration. These two are same one. Then the molar concentration of H plus and OH minus ion can be determined by finding the degree of ionization alpha. I repeat, here molar concentration of H plus and OH minus ions can be determined by finding the degree of ionization alpha at room temperature. The degree of ionization alpha can be calculated from the values of lambda phi, molar conductance of water at infinite dilution, Yes, here molar conductance at any free dilution and molar conductance at infinite dilution. The value lambda phi is given by lambda V, it is the product of specific conductance and volume of the solution. In this equation, this is the kappa specific conductance of pure water and the value of specific conductance at 25 degrees centigrade, it is equal to 5.0 into 10 raised to minus 6 ohm inverse meter inverse, and phi, it is the volume in cubic meters containing 1 mole of water. The volume phi is obtained by dividing molecular weight of water with density at 25 degrees centigrade, and which is 0.997 grams per centimeter cube. Therefore, we can calculate the volume. It is equal to molecular weight divided by density, and this ratio it becomes equal to 18 divided by 0.997. It is equal to 18.05 centimeter cube, and it is equal to 18.05 into 10 raised to minus 6 meter cube. Hence, lambda phi or equivalent conductance at a free dilution, it is equal to specific conductance 5.8 into 10 raised to minus 6 multiplied by the volume, here 18.05 into 10 raised to minus 6, and it is equal to 104.7 into 10 raised to minus 12. This is the value of lambda phi. The molar conductance of water at infinite dilution is sum of molar ionic conductance of H plus and OH minus ion, and by adding these values we have, this is the molar conductance of water. Then the degree of ionization alpha at 25 degrees centigrade, it is given by the ratio of lambda phi divided by lambda 0, and putting these values as 1.047 into 10 raised to minus 10 divided by 0.0542, it is equal to this value 0.192 into 10 raised to minus 10, and therefore alpha it is equal to 0.193 into 10 raised to minus 8, and it is equal to 1.92 into 10 raised to minus 9. Again, we can find the concentration of water in mole per decimeter cube, and it is given by C, it is equal to 1000 divided by molecular weight, and molecular weight, all of you know, it is equal to 18, and this ratio becomes equal to 55.55 mole per dm cube, or mole into dm cube raised to minus 3. Now the ionic concentration of H plus ion and OH minus ion, it is calculated by putting the H plus, concentration of H plus, it is equal to concentration of OH minus ion, and it is equal to alpha into C, where alpha it is the degree of dissociation and C is the concentration. Already we have calculated alpha value here and concentration value here, and by taking the product we get the ionic product of water as here 1.06 into 10 raised to 7, and H plus ion concentration again into 1.06 into 10 raised to 7, and the product of these two it becomes equal to 1.1 into 10 raised to minus 14, and this is the value of ionic product of water. Here, this is the one of the most important application of Kohlrausch law in the determination of ionic product of water. Though this application is important, it requires the knowledge of specific conductance, how to calculate the concentration and degree of dissociation. And by putting the values of alpha, then concentration, we can find the concentration of H plus, concentration of H minus ion, and taking the product, that means Kw, it is equal to concentration of H plus into concentration of OH minus ion. We find the ionic product of water as 1.1 into 10 raised to minus 14. This is the value of ionic product of water. And here we have seen the important application of Kohlrausch law. I hope you will understand, and if you don't understand, you may ask me. I will solve your whole problems. Then on this topic we have arranged one test on a Google and you have to attempt it. Again, those who are watching videos carefully, they can understand well, but those who don't have time to study, they may watch videos carefully, ask your problems, get them solved and study well. And best of luck for your assignment or quiz. A simple quiz will be there on this topic, probably on the Sunday. So prepare well, and if you have any doubt regarding any point, you may call us and get your problem solved. Thank you.